So, in part 2 of this tutorial, we'll be looking at deep foundations, specifically piles in clay soils. And also we'll be introducing two layers into this example so you can see the effect on the problem when we have more than one layer of soil that our pile is in. So the example we're going to be looking at here then, we have a 10-meter deep pile, 1 meter in diameter. Again, we're looking at a circular pile. The unit weight of this pile is 22 kilonewtons per meter cubed, and we have two layers that the pile is in. The first layer, 6 meters from the top, 6 meters deep, is soft clay, and the cohesion of this soft clay is 25 kilopascals. The second layer, 4 meters from the bottom of the first layer, is a stiff clay, cohesion of 125 kilopascals. Both unit weights of the soft and stiff clay has a gamma sat, or a saturated unit weight, of 18 kilonewtons per meter cubed. Now, an important note for clay soils, the limiting capacity is often controlled by the short term, i.e. the undrained conditions. Now we're going to be working through this example as we did last time, looking at the base resistance, the shaft resistance, the weight of the pile, and then ultimately calculating the ultimate actual load that the pile can take. Starting with the base resistance, as before, PBU equals AB bracket FB plus P0, FB being the net ultimate resistance, but for clay, FB is equal to NC times CU. So if we just substitute that into the equation above, we have PBU equaling AB bracket NC times CU plus P0. Now, it is conventional to take CU as CUB, where CUB is the undrained shear strength of the soil at the pile base, and to assume the undrained internal friction angle is 0. The value of NC can then be obtained from Skempton's chart, and the Skempton's chart is for when the internal friction angle, or the undrained internal friction angle, is equal to 0. So let's start calculating the base resistance. AB is the area of the base, and so pi r squared, pi times 0.5 squared equals 0.785 meters squared. P0 equals the overburden pressure at the base of the pile, so it's gamma times the length of the pile, so that's 18 times 10 equaling 180 kilopascals. Our NC value can be read off this chart here, and we can obtain a value of 9. So our NC times CUB equals 9 times 125. Now CUB, as I said, is equal to the undrained shear strength in the soil at the base of the pile, and you can see here in this scenario that the soil at the base has a CU value of 125. We're not using the properties of the soft clay because the soft clay is not at the base of the pile, the stiff clay is. So 9 times 125 equals 1125 kilopascals. So we can put that all in now into our PBU. So PBU equals 0.785 brackets 1125 plus 180 close brackets equals 1024 kilonewtons for the ultimate base resistance of this pile. So moving on to shaft resistance, PSU equals FS bar AS, as before, FS bar being the average ultimate side resistance per unit area, AS equaling the surface area of the pile shaft in contact with the soil, but as I said, it works slightly different for clayey soils. Now you may have seen the equation before, FS bar equaling this equation here, and obviously it is to do with integration because we have this symbol here that we should all be familiar with. Personally, I don't like to look at that kind of equation. Integration isn't my kind of thing, so I steer clear from it. So I'm just going to go through it how I approach the question. I know that Fs is equal to alpha times Cu times Z. Now alpha is a reduction factor and is specific to or dependent on the value of Cu, the undrained shear strength for the clay in question. But we need to remember we have two layers that the shaft surface area of the pile is in contact with in this problem, so we need to consider both, and that's just simply a case of Fs equaling alpha 1 Cu1 times Z1 plus alpha 2 Cu2 times Z2, and this could go on for as long as we like, but we only have two layers that we need to think about in this question, so it will stop here. Now we want Fs bar, we've only got Fs, so we want the average, so we need to times this all by 1 over L, sorry, to give us the average, and then we can substitute this back into our PSU equation, so we can have PSU equals 1 over L brackets alpha 1 Cu1 Z1 plus alpha 2 Cu2 Z2 close brackets times AS. Now our AS in this scenario, due to it being circular, is calculated by pi dl, and now it's just simply a case of putting numbers into the equation. So 1 over 10 close bracket alpha 1. Now our alpha 1 refers to the top layer of soil in this problem, so if we look at this chart here, we know that our Cu is 25 kilopascals for the first layer, so read off this chart as a value of 1. It doesn't intersect with the curve, so it defaults as a value of 1 for the reduction factor. So it's 1 times 25 times 6 plus alpha 2. Now alpha 2, we're using 125 kilopascals off this chart, and we should get a value of around 0.43 for the reduction factor. Hopefully you get something similar. So 0.43 times 125 times 4 close brackets AS. So you should attain a PSU value of 1147 kilonewtons. Moving on to calculating the weight of the pile, we know W equals the volume of the pile times the unit weight of concrete. So again, because the pile is circular, W equals pi times r squared times L times gamma C being the unit weight of concrete. So we have, when we put the values in, a weight of the pile of 173 kilonewtons, and then last step, we know that ultimate bearing capacity, Pu, is equal to PSU plus PBU minus W. So it's just a case of substituting in the numbers now. 1147 plus 1024 minus the weight of the pile, 173, equaling 1998 kilonewtons as the ultimate bearing capacity of this pile. So in part 1 and part 2 we have looked at piles in clay and sand separately. In the next video we will look at an example where the pile is situated in sand and clay layers, and we'll see what effect this has on the design of our pile. Something to ponder though for part 4 of this tutorial. Let's just give ourselves a scenario. We have an oil rig out at sea. The pile foundations are partly above the seabed and partly penetrating the seabed. What effect do you propose buoyancy will have on PU, the ultimate bearing capacity of the pile? This is something we'll be answering in part 4, but something for you to think about for now.